Good evening, Carolians. This is Exploring the Solar System Part 4, Exoplanets. I'm going to be saying a little bit about why we look for exoplanets and then how we actually find them and how we go about looking for life and where things are heading in the near future. So we can ask ourselves, is our solar system typical? In other words, are there other solar systems that look like ours, or if not, at least are there other planets that look like the Earth? Is there life elsewhere? We know that there might be life on planets other than those that are Earth-like, but that seems like a good place to start. And perhaps studying other solar systems will help us to understand our own. So there are a number of different ways that we can find planets around other stars. There are basically 5 methods. The first is radial velocity, the idea that we can look for the wobble of a star produced by an orbiting planet, and we can see that spectroscopically, and hence we can actually find very small wobbles of a star, even from stars at a great distance, by using the power of taking the light from the star, breaking it down into the spectra and looking for a Doppler shift of that star. Second discovery method is transits, looking for the shadow, in other words, the drop in the output of light caused by a transit of a planet in front of the star. Those 2 methods alone account for a very large fraction of all the exoplanets that have been found to date. But there are other methods. For instance, becoming more popular these days is direct imaging. The idea being that if you can block the light from the star, then maybe the much fainter light from planets, which could be thousands if not millions of times fainter, if you block the light, the direct light from the star, maybe you can see the planets directly. And a fourth, less common method is gravitational lensing, called microlensing if we're looking at the bending of light from a distant light source produced by a planet round a star rather than by the star itself. And similarly, the 5th method, also very unpopular at the moment for finding exoplanets, but who knows about the future, astrometry. In other words, not looking for spectroscopic evidence of a star wobbling because of an orbiting planet, but looking directly for the wobble in the star. In other words, if you can measure the position of a star accurately enough, which the Gaia spacecraft can do, then perhaps you can see stars moving because of the orbiting exoplanets. So I'm going to say something about methods 1, 2 and 3. I'm going to skip over 4 and 5, but they will be in a handout that I'll make available to you later if you want to check on those. So firstly, method 1, radial velocity, responsible for more than 1,000 planets to date. This particular animation indicates that if a star has an orbiting planet, then because of the motion of the planet around the star will wobble. In other words, the 2 are actually rotating around their common centre of gravity. So depending on the mass of the planet, the star will come towards us or away from us, and so there will be a Doppler shift. That particular animation sort of implied that the light of the star would turn red if it's moving away from us, or turn blue if it's moving towards us. That's not really quite how it works. Perhaps a better indication is this spectrum in the bottom right of this animation indicates what you would actually see. You won't necessarily see the light from the star change colour, but if you look at absorption lines indicated here by these black lines, they will appear to move backwards and forwards in the spectrum. In other words, they will be blue shifted or red shifted as the star comes towards us or moves away from us. So it's not really the change of colour in the star, it's the fact that characteristic absorption lines in the star, if they can be measured, will be seen to move towards the red or towards the blue, backwards and forwards as the star wobbles because of the existence of the exoplanet. Method number 2 is looking for transits, and this is a situation where we have to have the planet moving in front of the star. We can't see what's going on as seen from above, but if a planet moves in front of the disk of a star, then we get a drop in the light output, as indicated by that little cartoon on the bottom left. showing you the amount of light coming from the star as a function of time. If we get a characteristic dip, then we can deduce the existence of an exoplanet, especially if we see that dip more than once. If there's simply a decrease in the light of the output of the star, we have to worry about whether the star is a variable star or if there's a sunspot on the star. But if we see it repeatedly, then we know it's due to an orbiting planet. One of the advantages of the transit method is that the size of the planet will determine how much light gets blocked, and hence the depth of the dip we see in the light output tells us how large the planet is. So the previous method, looking for a wobble spectroscopically, the more massive the planet, the bigger the wobble. So spectroscopic indications of the mass of the planet will tell us mass, but here we're looking at the size, a different measure of perhaps the same planet. And if we were to look at, for instance, a system as seen from above, this doesn't work for transits, but there's the system as seen from above. If we see it from the side, then we see the transits. And if we have multiple planets, we might see multiple transits, as indicated by the light curve on the left. When planet number 2 and then planet number 3 come in, you can see we get a more complex light curve. And it can be quite complicated for systems in which we have 3, 4, 5, 6, 7 planets to try and work out what is going on. But that can be done if we have good quality data. So the transits give us the size. The radial velocity method, or the wobble method, gives us a measure of the mass, because the larger the mass, the larger the wobble. With transits, we can see an indication of how it actually works here, because we very rarely get a data set like the white line. We get something more like the blue curves, and we have to fit it to the best model we have as to what we would expect the light output to look like. So we have a data set and we fit it to particular possibilities, and from that best fit we deduce the size of the planet. If we have a look at actual data, here's data from JWST, and again we see the relative brightness here. When the planet is not transiting, we get effectively constant starlight, and then we get a dip as the planet transits. And notice that the depth of the dip here is only some it drops to maybe 98.5%. So the dip here is only 1.5%. Larger planets will give a larger dip, but it's not unusual to find some of these dips might only be barely 1% of the output. So we need the most accurate measure we can of the output of the star to tell us exactly what the size of the planet is. The third method, which might be more popular in the future, is direct imaging. If we use an occulting disk to actually block the light of the star, then the very dim light of the planet might then become visible. If I just run that little animation one more time, the star is simply too bright to actually show us the planet, but if we occult the star, then the fainter planet might then become visible. Otherwise it would be lost in the glare of the star itself. This hasn't been used to find that many planets so far, but it is likely to become more popular in the future. Here we see a number of examples of direct imaging where the star itself, indicated by the little star symbol, has been blocked out by that black disk, and we can see 4 objects orbiting around the star. This video is repeating. We see an object quite close moving fast and 3 other dots at greater distances, indicating planets that are not moving quite as fast. Let me just run that animation one more time. So here we are fortunate enough to be viewing the solar system, the star system, from above, and hence we can see the planets moving as if we were looking down on the top of our own solar system, or on top of an orrery. One advantage of direct imaging, unlike the transit method, which only really works when we've got a possibility of a transit or an eclipse of a planet, direct imaging could in principle work either when we are face on to the stellar planetary system, or indeed when we are side on, as seen by this situation where we can't see the planet except when it appears from behind the occulting disk, and then we see an indication of the planet coming out each side. again, let me just run that run that animation one more time. So we get direct imaging even though the planet might be transiting or it being eclipsed by the star itself. So we have the possibility of spectroscopically seeing the wobble of a star, which will determine its mass, seeing the wobble of the star giving us the mass of the planet, the transit of the planet giving us the size of the planet, and it's also possible to get the periods from direct imaging as well. James Webb has tried a number of direct imaging experiments by, again, occulting the main star. Here, the bright star Fomalhaut has been occulted by the black dot in the centre. And here we don't see a planetary system, but we do see a rather dusty debris disk, indicating that this might be a very early formation of a protoplanetary disk. Perhaps we're looking at an asteroid belt and a Kuiper belt or something like that. It was thought in the early days, the little inset there in the bottom right indicated that maybe we're seeing the formation of a planet, but now it looks like that particular little density knot in the disk has disappeared or dissipated, and it's not visible at all wavelengths. So perhaps that isn't a planet actually being formed, it just happens to be a slightly denser part of the protoplanetary disk. Fourth method I'm not going to mention, that's a gravitational effect of microlensing. And the fifth method, as employed by Gaia, is if we are looking at the positions of lots of stars very accurately, which is Gaia's principal job, then it might be that we can see over a period of time a star wobble in its position on the sky, indicating that it has a massive planet orbiting around it. So Gaia's job was to map out stars, but as a secondary result, we might actually pick up a few exoplanets in the process. So the methods I've been talking about, especially methods 1 and 2, radial velocity giving us wobble and hence the mass of a planet, and transits looking at the shadows and the dip in the light output, the depth of the dip indicating the size of the planet. When we use all of this information together, if we study a system that can be studied by spectroscopically looking at the radial velocity Doppler shift as well as looking at the dip in the light from the transits, then we get an indication for the same system of the mass of a planet and its size. And also spectroscopically, in principle, we can look at absorption in the atmosphere as well. But one important aspect is if we have the mass and the size of the planet, then by combining those two numbers, we effectively get an estimate of the overall density of the planet. And if the density is very low, we might well be dealing with a gas giant. And if the density is very high, then perhaps we're dealing with a more rocky planet. Hence, by using the mass and the size in combination, the density effectively gives us the type of planet we're dealing with. If we know the period, then assuming we have an idea of what type of star we're dealing with, and generally speaking spectroscopy does tell us about the type of star which the planet is orbiting, then if we know the period of the planet's orbit, we can get an idea of how far it is from the star, and hence we can get an idea of what its equilibrium temperature would be. And that will effectively tell us whether we're dealing with an ice planet or whether we're dealing with a lava planet. So we have a lot of information in principle if we can study exoplanets by more than one technique. And we have found lots of them. This graphic indicates something like 1,000 different exoplanets, all shown approximately to scale, where they are arranged left to right on a temperature scale. The ones with the lowest equilibrium temperatures on the left and the highest temperatures on the right. So these are the temperatures that an object would reach, ignoring the fact that if a planet like the Earth, for instance, has an atmosphere, then that will tend to raise its temperature because the atmosphere will form a sort of blanket, if you like, and keep the planet a little bit warmer. So these are just the equilibrium temperatures, the temperature you would expect an object to come to if it was simply at that distance from its host star. So all of these planets are approximately to scale. And if we look in the very bottom left, let's just blow that up a bit so we can see it a little more clearly. Here we can see some planets, including our own Jupiter, Saturn, Uranus and Neptune. Of course, they aren't actually exoplanets, but our own planets in the solar system are mixed in with the exoplanets just to give us a sense of scale. If we were interested in which sort of planets might be habitable in the sense of which might have liquid water, which is thought to be the most likely instance in which we can expect life to evolve, not the only instance, but why don't we start with the habitable zone and then we can think about, for instance, whether or not moons of other planets might be places where life can exist. So if we stick with the habitable zone, at what distance from the host planet would we have to be in order to give us liquid water? Well, we find that quite a lot of these exoplanets would sit outside the habitable zone, and we can eliminate all the ones that are too cold on the left-hand side and all the ones that are too hot on the right-hand side. And we see that the habitable zone on this scale looks very narrow. Remember, the overall range here is very low temperatures on the left and very high temperatures on the right. If we look at where some familiar planets are, for instance, there's Mars looking rather cold beyond the habitable zone in terms of distance, so a bit too cold. And on the near side, there's Venus, which is getting a little bit too warm. And no surprise, of course, Earth is within the habitable zone. But if we look at a few of these, we can pick out a few interesting planets amongst these thousands of planets that we've seen in this infographic. Bear in mind that the total number of exoplanets we found is something between 5,000 and 6,000. So this is actually only a small selection of all the planets that we know of. In the bottom left, we have the system Proxima b, only 4 light years from Earth. This came as a little bit of a surprise, not least because if we think of our immediate neighbour as having planets, what's the chances that our immediate neighbour has planets if planets are rather uncommon? This gives us a good indication that a large fraction of stellar systems will have planets. Some dwarf stars, some larger stars. It looks like planetary systems are much more common than we first thought. In the top left-hand side, there's a planet that's become known as Methuselah because it appears to be orbiting a star that is 12.7 billion years old. This was found spectroscopically. So if the star is 12.7 billion years old, then it seems very unlikely that the star could have existed for billions of years and then a planet formed. So it looks like planets can form very early on in the universe because this planet appears to have formed barely a billion years after the Big Bang. So this gives us an idea that not only the range of star formation and galaxy formation, this gives us an idea that planetary formation is by no means unusual. Planetary formation seem to have occurred almost as soon as stars formed. In the top right there, that's one of the hottest planets that we can conceive. It's got a surface temperature of more than 4,000 Kelvin, which I find rather hard to believe. Bear in mind this is an equilibrium temperature, not necessarily a surface temperature, but this star is close enough to its host. This planet is close enough to its host star such that it's believed that its surface temperature would be thousands of Kelvin. So it's difficult to believe anything much can exist on a planetary system like that. Still on the extreme right-hand side, but in the bottom right-hand corner, perhaps you notice that planet looks a little bit distorted. That's not your monitor or your screen. That is an egg-shaped planet. This one is close enough to its host star, a mere 4 million kilometers. Remember, the Earth is about 150 million kilometers from its star. This planet is close enough to its star that it is almost certainly egg-shaped because of the tidal forces being raised on the planet by the star itself. What other interesting exoplanets do we have in the exoplanet zoo? In the top right quadrant there, we have the planet going under the wonderful name of HATP67b. It's something like 10 times the size of Jupiter, but appears to have a mass less than Jupiter. Remember that we can get the mass from the spectroscopic wobble and we can get the size, the diameter, from the transit method, and in this case we've measured both, and it appears to be 10 times the size of Jupiter but less massive than Jupiter, which means its density must be very low. It's been likened to, well, it's probably about the same density as marshmallow. That is a very low density material. And although HATP 67b is a bit difficult to get your tongue around, I think the prize for the best name for a planet, the best name for an exoplanet, I think has to go to Coconuts 2b. What a great name, Coconuts 2b. Coconut stands for Cool Companions on Ultra-Wide Orbits, a little bit of a contrived acronym, but you can see its distance from its host star is 7,500 AU. So 1 AU is the distance from the Earth to the Sun, so this is 7,500 times further from its host star than we are from the Sun. So instead of going round its star in 1 year, its year is something like 1 million of our Earth years. It's difficult to believe a planet can exist that far from its host star, but it appears to be possible. Perhaps one of the weirdest exoplanets in this exoplanet zoo is LHS 1140b, a so-called eyeball planet. It appears to be an ice planet, but it also appears to be close enough to its host star to be tidally locked. That seems a little unusual. It depends on the flux of energy coming from the host star. So it appears to be an ice planet, but because it's tidally locked, one face is always facing the host star. And that means it's quite possible that the side closest to the star has actually had its ice melted, as indicated by this artist's impression. So you might end up with an ocean, a small ocean, surrounded by the rest of the globe of the planet being ice. And so you get this rather weird eyeball effect. Just a little speculation based on an artist's impression, but it's based on the known characteristics of this particular planet and its distance from its host star. So there are some interesting possibilities out there. I've already mentioned that some exoplanets have been found not necessarily by spacecraft that are explicitly looking for discovery of exoplanets. For instance, Gaia's mission is to map out the positions of stars in the Milky Way, and as a side effect, it's been looking at positions of some stars which appear to be going in small circles or ellipses, indicating that we've got exoplanets going around them. And James Webb Space Telescope, one of its jobs is to look at early planetary formation, and so its job is to block out the light from stars and see what it can see of protoplanetary formation. And as we've already seen, it can in principle directly image exoplanets. But there are quite a few missions which are explicitly looking for exoplanet discovery and exoplanet study. There are a number of these. Perhaps you've heard of Kepler, that's found thousands upon thousands of planets through the transit method. But fairly shortly there'll be two new missions, an ESA mission called Plato in the top right there, and the middle bottom a NASA mission called the Nancy Grace Roman Space Telescope. These are due for launch in 2026 and 2027 respectively. I believe they're still on track for those launch dates. In the much longer future, there's also the possibility of a so-called Habitable Worlds Observatory indicated in the bottom right, but notice that the launch date is many, many years away. One interesting development is the idea that the Roman telescope, the Nancy Grace Roman, or Roman for short, the Roman telescope won't necessarily have an occulting disk as is common with other telescopes to block out the light from a distant star, to directly image other planets. The idea is maybe you can use an occulting disk which is external to the telescope itself, a so-called star shade. You have the telescope and the star shade as two separate entities. Once launched, they will separate, and then the star shade will unfurl into a huge 100-meter diameter shade, which will then separate from the telescope at a very large distance, something like 50,000 kilometers away. And when the star shade is at that sort of distance, it will be steered to block the light from a distant star, and as a result allow any exoplanets around that star to be directly imaged by the Roman telescope. The advantage of a star shade compared to having occulting disk inside the telescope is that by having a star shade external to the telescope, none of the light from the star enters the telescope itself. Whereas if you allow starlight to enter a telescope, even though you try and block it to see the planets themselves, some light will still be scattered in the optics of the telescope and make the planets more difficult to see. So this is the preferred method, as long as you can steer a star shade and position it accurately relative to your telescope. How would we go about looking for life? How does the JWST go about looking for interesting planets and interesting atmospheres? Well, we've seen in the transit method that if we've got an eclipsing or transiting planet that's in the plane of the observation, then we can see the planet move in front of the star and we get a dip in the light. But we also notice that the planet can go behind the star, which means if we look at the spectrum of the star, or the star and the planet, when the planet goes behind the star, we lose the spectrum from the planet. And so if you look at the difference in the spectrum before and after an eclipse, you can get an idea of what light the planet was emitting. And also, when you go into a transit, as indicated here, it is possible that the light from the star shines through an atmosphere, if there is one. And therefore, it is possible that the atmosphere will absorb some of the light coming from the distant star, the more distant star. And this we can see in the light here from JWST. So here we're looking at starlight. We're not able to resolve the planet, but here we can look at the starlight, and when the starlight gets blocked by the transiting planet, then the starlight effectively drops, as we saw before. But if we do this at different wavelengths, let's blow up that region in a little more detail, we can see the depth of that transit actually varies depending on which wavelength we're looking at. The different coloured dots here correspond to different wavelengths of infrared light. And those wavelengths of infrared light are chosen such that we know that certain gases that might be present in the atmosphere of a planet will absorb certain wavelengths. And so if you look at the different depths of this transit dip, we can get information about which molecules are present in the atmosphere absorbing the light. And this is what the James Webb Space Telescope has been doing for a number of different planets. And here we can see some data from a particular planet. This one happens to be WASP-39b. And by looking at where the bumps and the dips of these spectra are, we can effectively start to identify, do we have carbon dioxide? Do we have water? In this case, we seem to have some sodium, some water, some carbon monoxide, some carbon dioxide. We are on the lookout for instance, oxygen and methane and perhaps dimethyl sulfide and other molecules which would be indicators of life. So still early days, but it is possible for James Webb to work out what molecules are present in atmospheres of distant planets. Hence the idea of finding life is definitely a possibility. Let me finish with this little animation giving an idea of exoplanets that have been found over the past few decades. Here we're plotting planet positions. Mass is on the vertical axis in mass of Jupiter, so there's Jupiter itself, opposite 1, and there's Earth, only a few % of the mass of Jupiter. And on the horizontal axis, we've got the orbital period in days. So there's 300 or so days for Earth, there's something like 10 years for Jupiter and 30 years for Saturn. So here we've put the solar system objects in just to give you an idea of where these exoplanets are being found. If we run the animation, and we'll get now a dot for every exoplanet that's been found. To start with, not much in the 1990s, but then we start picking up some radial velocity. In other words, spectroscopic wobble is being detected. When we move into the late noughties, as soon as Kepler is launched, we start to get lots of exoplanets that are found by the transit method, these blue circles. And you can see that as time goes by, year by year by year, we are picking up hundreds and thousands of exoplanets. By 2024, we notice that there are some 5,000 or so of them. When we look at an image like this, we might think, well, there appears to be preferred places where we find planets, this sort of mass of Jupiter at this sort of distance, and there appears to be a clump of them down there, and relatively few over here, and lots of them over there. But we have to be very careful due to something called observational bias. In other words, it's easy to pick up more massive planets. It's much easier to see massive planets than it is to detect less massive planets. And it's easier to detect planets when they are closer to their host star, in other words, on the left-hand side of the diagram. So anything up here is relatively easy to detect, but anything down here is relatively difficult to detect. Hence, we shouldn't take this graph of what have we found so far as necessarily an indication of what is actually out there, because it's biased by the fact that some things are easier to do, some experiments are easier to do, some observations are biased towards the ones that are easy to do. Large planets close to their stars are easier to find. So it's perhaps not surprising that we haven't found very small planets like the Earth a long way from their host stars. But the systems that are going to be coming online, the new missions, Plato, etc., the Roman telescope, more from the James Webb, might well indicate that we find more and more planets towards the bottom right of this diagram, more and more Earth-like planets. So if I've piqued your interest, you can find more. You can find a lot more by going to nasa.gov. They have a very nice exoplanet dashboard there. And the NASA Exoplanet Archive indicated there essentially gives you specifications, all of the details you want to find about every exoplanet that has been discovered to date. And a reminder that there are various missions coming online very soon. The ESA Plato mission in 2026, the Nancy Grace Roman Space Telescope from NASA in 2027, and on the much longer timescales, the Habitable Worlds Observatory looking for Earth-like planets in perhaps decades to come. Don't worry about remembering or writing down these links. I'll make them available to Mike and Jim after the talk. So if that has piqued your interests, go away and find out more about these thousands of exoplanets that are out there. Thank you very much for listening.
Thank you, Steve.